Hey guys, I'm Drew from Three Sigma, and I lead business development here for the team. So excited to go through this presentation with you on our newest product, our Crash Data. So we are Three Sigma, and we are assessing vehicle territorial risk. How do we do that? Well, that's what we're going to talk about today. So I think this is a pretty generally well-known statement, but 52% of accidents occur within 5 miles of the driver's home. But insurance carriers today currently have limited capability to act on this. Okay, what does that mean? We're going to dive into that in this presentation today. And to address that, we're going to talk about four key areas. So we're going to talk about the current approach. We're going to talk about some problems that occur within that methodology. We're going to talk about our data, what it looks like, the depth of our data, and then we're going to talk about how we leverage that data to enable our risk modeling. And then we'll talk about some future steps that we're rolling out as well. So let's jump into it, right? First problem with the current approach is data sparsity, the lack of data, really. Carriers often use data from their previous claims to evaluate the risk with different locations. Okay, the problem is there's not one carrier that has all of the data, right? If you take a look at the state of Ohio, right, that's where myself, my co-founder Sergey, were from. If you look at the different carriers within that state, you see that even the big carriers still lack a large amount of crash data. So insurance carriers use their own crash data to make a lot of assumptions. However, even Progressive in this case here, just over 20% of the data, let alone all of these smaller insurance carriers as well. So how do the smaller insurance carriers get the data? Okay, you may have heard of ISO. Most companies can, reach out to ISO and compile their data, share their data, and get access to more data as well. However, ISO is still lacking 30 to 50% of a state's data. Okay, and with that, there's a lead time. It takes a while to gather the data and then report it and generate it and pass it out. So in this case of the state of Georgia, if you only have 30% of the data, this graph could look much, much different. Right? We see a general increasing trend, but we see it spikes with the seasonal cycles, and then a very large dip and recovery now since COVID. However, you would miss a lot of this clarity if your data points were on a larger time cycle, and also if you only had 30 to 50% of these crashes, we don't really know what it would look like exactly. So that's a problem with that approach. Now let's move on to talk about issue two, subsidization, right? Counties encompass large geographic regions with significant variability in the demographic within those boundaries. So this is addressing the current county approach that many carriers use. Let's go back to Ohio. So Franklin County is where Columbus is, and it's a much broader area of the metropolitan area around Columbus. Okay, 1.3 million people, 540 square miles. However, if you take a general average of all of the crashes in the area, you get a number. And if you look at it from a more granular perspective, you'll see the safest areas have 5 to 10 times lower than the riskiest areas, 5 to 10 times less crashes that still fall within those county limits. So if you are to generalize that the average person is likely to get in a crash based on the county average, you are potentially either charging that person, if they live on the outskirts, far too much to be competitive, or if you're looking at that on someone who lives in a riskier area, maybe you're undercharging them. So there's opportunity there to increase those loss ratios. So you could use zip codes, right? However, zip codes were designed for mail delivery, right? They're also not representative, not very well representative of population or high and low income areas. They're better than doing a county approach, but there's still yet a better way. So let's talk about population data as well. So carriers normalize their population statistics, but the per capita car ownership can vary widely across a given state or county. Again, so if you look at total crashes within a given county, and then you make an assumption that the uh, given county has X amount of people in it, um, that can really skew your results when you look at Ohio again, and we look at different per capita vehicle ownership rates. So if you look at a rural county like Lawrence County in Ohio, they have roughly 1.3 vehicles per person. However, if you break that down and look at a vehicle ownership rate in Franklin County, which is where Columbus is downtown, you see almost 50% of that. All right, 0.6 vehicles per person. So again, if you're distributing the number of accidents based on the number of people, that can really skew the results. So it's not the best approach either. Okay, let's keep moving along here. So now let's get to the data, right? What does the data really show here? So we have created a database of 94% of all the accidents within the U.S., and we're diving into more of the granular details of the crash data as well. So we have over 85% of the total premiums within the U.S., and that's recently gone up just a little bit more. And we have vehicle level data on several states as well. And so our lag time or lead time for our data, in some states, it's pretty quick, about 3 months, so just the previous quarter. And then some states, the lead time by the time we can get all the data in and process and clean is about a year for us to publish that within our systems. Let's look at that a little more. So the main type of data that we're gathering is crash level data. This gives us the location of the crash, the time of the crash, some other interesting variables as well, such as the severity of the crash. But it's not just the crash data that is important to us, it's the vehicle level data as well, right? So it's one thing to know where the crash occurred, it's another to know where that car came from, right? This is what really sets apart our risk score. Knowing the riskiness of an area is one thing where the crashes occur, but then knowing where those vehicles originate from to tie that back to the policyholder is the real key here. And so we get a lot of data from the crash and the vehicle level data as well. And currently, I think we have about 10 states at the time of this PowerPoint, and we've got about 20 states now. And again, we're targeting states and working with states with the highest dollar premium first. So moving along, data accuracy. Okay, so how do we know our data is good data? Well, if we look at the data that we've gathered so far and we compare it with FARS, right? So the federal government, they maintain the Fatality Analysis Reporting System called FARS. It's a nationwide database that tracks fatal crashes. So it's very strict requirements. And if we look at our data, and so we mentioned the crash data, we have the severity of it. We also know if it's a fatality. We compare our number, summing up all of the crash data that we have, and we compare it to FARS, we're within a 5% margin 88% of the time. So we're right on the money when it comes to the accuracy of the data that we've developed. The accuracy comparing it to, or relating it to the total number of accidents within the nation. So this is something we're working on again when it comes to the third issue point to vehicle registrations. We have and are actively gathering much more vehicle level data and registration data, so where those cars came from and where they are located to help us with the normalization. Most of the time it is on a county level, and we're working to use census data to refine this even further into smaller chunks. So we've talked about the issues in the industry today. We've also talked about the data that we have gathered. And now let's talk about the fun part, right? Calculating that territorial risk score, predicting vehicle risk or vehicle driver risk. How do we do that? Okay. So we're going to break this down into a couple steps. The first step is obviously getting data. We talked about that. The second step here is aggregating the data. Okay. So compiling the list of all the crashes in the U.S. and the state and the counties, it can be a very large problem to look at here. And so we first want to aggregate that data and clean it up and assign it to a grid as well. And so there's different coordinate systems that you can use when you start doing the accident mapping. And there's a couple problems with some traditional methods such as a triangle or the square. Triangles, if you use a triangular approach to gridding out the US, triangles have 12 neighbors, and the distance of the neighboring triangle isn't always the same, right? They can actually differ in distance from the center, almost 2x, right? So that would skew the numbers quite a bit. Then you have squares, and squares have 8 neighbors. Again, the distance between the corners, the corner neighboring squares from the center square is again a little obtuse. So skewing the numbers again, when you look at severity, number of accidents, it's difficult to take an average of the neighboring square. So then you have the hexagon approach. So hexagons have 6 neighbors, and they're all equidistant from each other. Okay, so we take a hexagonal coordinate system. That's the system we use. And it was created by Uber. Google has their square method. And if you look at the square method again in different areas of the US or different areas of the globe, they have a lot of manipulation and stretching that can again skew your results if you're looking at accidents in a confined space. So in Amsterdam, you see it's a little longer in the rectangular direction vertically, and in San Francisco, it is pretty skewed. However, if you look at our approach again with the hexagons, virtually the same in the same square footage area, which is key. Hexagons have some interesting properties as well. So you can have a hexagon here over a city block, and then you can combine multiple city blocks, multiple hexagons into a larger hexagon, and again you can go into larger hexagons yet again. This helps us out with a lot of key challenges in determining the severity of different geographic areas based on the number of crashes within those areas. And so we'll talk about that here in a bit. So now we defined our aggregate system, right? We're using the hexagons. And now let's talk about aggregation. So what we then do is we then take all of our crash data that we have and we plot it on the US street maps essentially, right? So you can see all the crashes that are occurring in this given location, and we add our gridding pattern on top of that, right? So that shows us with, that really aligns the number of accidents to a geolocation in a hexagon in a neighborhood, and the number of crashes within that hexagon help us correlate and determine the severity of that region. And so we start very, very small, and we run our model on multiple different layers or sizes of the hexagons to generate our true severity there. And we'll talk about that here in the modeling category. So if we do that, you might have some areas that don't have a lot of crashes, right? Some rural areas, some areas that maybe don't have a lot of people in, and there's not a lot of crashes, but they also might have a crash or two. And how do you accurately determine the risk of that area if there's a lack of data? That's where spatial smoothing comes in. And so as you decrease the aggregation resolution, you might run into some of these challenges. You get more variance in the bins. And so we run a smoothing algorithm that helps distribute the riskiness of the neighboring squares or hexagons into those areas. So here's something interesting from our data. So this is again looking at the state of Ohio. So these are crashes from Powell, which is where I grew up, funny enough. And when you correlate the crash data to the vehicle data, you get where the crash occurred, but also where that driver's from. So when we look at the state of Ohio, if we just look at Ohio here, and just look at the city of Powell, Ohio, in 2023, these are all the locations that those drivers who live in Powell got into an accident. So you see that several of those drivers got into an accident. Looks like relatively, pretty close to Columbus, probably downtown or, on the outer belt, I would expect. Then you see some got in an accident in Cincinnati, and some drove to Chillicothe, and so on, right? The green or the orange here is the number of accidents, or an accident from Powell, and the red here is actually a fatality that occurred from Powell. But what does this mean? It's hard to look at this and make any assumptions from it. So our problem was, people from our hometown, where do those cars get in accidents? So if you look at it on a map and you look at the dots rather than all of the lines, you see here that if we take our assumption from the beginning and you look at a 5-mile radius around Powell, not everyone gets an accident within that 5-mile radius, right? A lot of accidents, maybe you're skewing the neighboring counties or hexagons because the driver comes from Powell but crashes somewhere else, right? So how do we tie that back together? Also, what you'll see here is that most accidents align on some of the major highways in the region, right? No one's going to Marysville or Delaware and driving out in the farm fields and getting in crashes, although there is some. Most of the crashes are people going from less urban areas to more urban areas for work, for for activities and such. So naive smoothing techniques wrongly smooth. They wrongly assume equivalent crash likelihood in all directions, right? So you don't just want to take a given hexagon and assume that the risk of a crash in this hexagon is very similar to this hexagon. You have to look at multiple factors here going towards the urban areas. So what does our model really look like? So this is the rough architecture of our model. We have the crash data and the vehicle registration data, right? That goes into temporal split, where we split every 2 years. And then we also split into severity. So we're essentially running this 5 different times based on the severity of the different accidents, okay? Then we aggregate those into our hexagons that we talked about. And the first one is only 36 square kilometers. And then we have a little bit bigger hexagons as well to help us with the voids in the data and provide a more accurate approach. And then we smooth the data, and to do that we use our XGBoost algorithm to help us predict the number of crashes and smooth the data points out, and then we get our model. So if we take a look at Fulton County, Georgia, and I just want to dive into the real impact this is having, okay? So if you look at 2022 data, and if you take a county approach, you see the hexagon image on the county average diagram right there, right? If you then use our binning techniques and look at all the crashes from 2022, we can predict and look at the regions that had the highest level of severity, or those that present the most risk. Then we make a prediction on what 23 will look like, which is our prediction right there, the middle image, and the actual crashes that you see. Now, in this, we normalize by the number of vehicles, and you can see our prediction very closely matches the actual crashes that did occur. Let's keep moving along here. So if you look at not just Fulton County, Georgia, but the entire U.S., you see a county baseline with a normalized RMSE number of 0.286. And if you use our multi-tiered approach with the different hexagons and XGBoost for the smoothing, you have a normalized RMSE value of 0.09. So, predicting costs, currently only looking at the property damage crashes. However, we are seeing a significant lift in this new approach. So further improvements, we're further developing our smoothing algorithm to better estimate registration locations for drivers and crashes. It's critical for analysis in states that are lacking vehicle level crash data. But that is one area we're making a lot of headway on today. We use vehicle level data to further refine our cost estimates. And then there's opportunities to pull in medical, legal, and vehicle repair costs in different counties to better estimate the costs. Because if your vehicle gets an accident in Columbus, Ohio, and you're going to a hospital in Columbus, Ohio, an attorney in Columbus, Ohio, and the car is getting repaired in Columbus, Ohio, those costs are likely to be much, much higher than if you're getting in an accident, outside of the urban area, maybe in Mansfield, Ohio, or Mansfield or Marysville, where it's more rural, and those rates are likely to be cheaper. Anyways, that sums up our presentation today on the territorial risk score and really what we do at 3 Sigma. So if you have any questions, feel free to reach out. We appreciate your time. Thanks.